The next application on the op-amp we are discussing is a log amplifier. As the name suggests, a log amplifier is something that it will produce the logarithm at the output. So output voltage will be proportional to the logarithm of input. So it will be doing the operation called a log. Of course, it is an operation amplifier. It will amplify your signal also. Now, we will see how you are getting output as the logarithm of input. See, this is the schematic of a log amplifier. Here, in the feedback path, you see you have a transistor. This transistor is essential, otherwise it will not produce the logarithm. So the feedback path contains a transistor for a logarithm amplifier. See, emitter of the transistor is connected to the output, collector is connected to the input, and base is connected to the ground. So it's just formed by placing a transistor in the feedback path of op-amp. Now see, what is the voltage of collector? The plus terminal is grounded. So the voltage at the positive terminal is 0. So by virtual ground concept, voltage at this point also should be equal to 0. If this voltage is 0, that means collector is also held at 0 potential or ground. Base is also ground. Now we go to the analysis of the log amplifier. So if I am writing the transistor voltage current relationship, you must have studied in your electronic circuit the voltage current relationship of the transistor. It's given as IC is equal to IS into e raised to VBE divided by VT minus 1. Here, what is IC? IC should be the collector current. What is IS? IS is emitter saturation current. It is a reverse saturation current. You must have studied this term in the diode equation. So IC is the collector current. IS is the unknown terms I'll just write for you. IS is the emitter saturation current. Emitter saturation current. Now VB you know that base to emitter voltage. VT is the volt equivalent of temperature. So VT is actually volt equivalent temperature and it is actually VT, we can write it as, you must have studied KT by Q. KT by Q, where K is the Boltzmann's constant, T is the absolute temperature, and Q is the electronic charge. K is nothing but it is the value of 1.38 into 10 to the power minus 23 joule per Kelvin. So K is the Boltzmann's constant, T is the absolute temperature, and QT is the absolute temperature, and Q is the electronic charge. Electron charge. Now take this equation. So if I am readjusting this equation, so I am just going back to the equation. I am readjusting the equation. I can write this as IC divided by IS plus 1. This one I am taking this side should be equal to e raised to VBE divided by VT. Now this IC is very small. IC with reverse saturation current. It should be very small value. So IC by IS will be very large. So I can write this IC by IS plus 1 is almost equal to IC by IS itself. So this expression again I can rewrite as IC by IS should be equal to e raised to VBE divided by VT. Now, if I want to change the exponential, I have to take natural logarithm on both sides. So, I am taking the natural logarithm ln. ln IC divided by IS should be equal to VBE divided by VT. So, what is VBE? Cross multiplying, I will be getting VBE is equal to VT into ln IC by IS. Now see here, what is base to emitter voltage? What is base to emitter voltage here? Base to emitter voltage is the output voltage. So base to emitter voltage I can write as VBE is actually equal to, it is emitter to base, right? Output voltage is emitter to base. So VBE will be equal to minus VO. VBE should be equal to minus VO. So here I can write as then VO. VBE is equal to V minus VO. It should be equal to minus VT ln IC by IS. Now see, what is IC? IC is the collector current, right? This is IC. Now what is this current? Say this current I can write it as, say it is I1. So what is I1? I1 is VI divided by R1. So I can write as I1 is equal to VI input divided by R1. Now there is no current flowing to the operation amplifier minus inverting terminal. So I1 should be equal to IC. So from this I can also write as here IC should be equal to I1. IC should be equal to I1. So IC is equal to VI divided by R1. IC is equal to VI divided by R1. So if I am substituting the value of IC here, VI divided by R1, I can write here minus VT into ln IC is VI divided by R1 into IS. So that is, but finally getting the equation as, here you be getting as VO is equal to, see here, minus VT into minus VT into ln VI divided by R and IS. So you see, output is come as the logarithm of your input. Output getting as the logarithm of your input. So this is the output expression. I'll write one more time here. V out should be equal to minus VT ln VI divided by R1 into IS. So this is logarithmic amplifier. Now just understand here the important thing over here. What is a function of capacitor? The capacitor across this NPN transistor is used to reduce the AC gain. The capacitor is used to reduce the AC gain, and the diode put here is for protecting the transistor against excessive reverse base to emitter voltage. So these two you have to remember, function of the capacitor and diode over here. Capacitor across the NPN transistor is used to reduce the AC gain, and the diode protects the transistor against excessive reverse base to emitter voltage. Now, here when we are giving design parameter, transistor diode, there is nothing to design. You have to design the value of R1 alone here. So there is a range that R1 should satisfy. R1 should be, the value of R1 what you are choosing should be greater than or equal to the maximum input voltage divided by the maximum IC current. It should be greater than that. Also it should be less than the maximum input voltage by the input bias current of this op-amp. So this will be getting in maybe in the kilo ohm range, this will be in mega ohm range. So you have to choose an R1 in between these two values. So that is the design constraint on this log amplifier. So this is about log amplifier. Remember, log amplifier output will be proportional to the logarithm of your input. Thank you.